So last time we started this question, we could not complete it. So let's complete it now. So this question has given you two graphs, two curves, AB and AC, and the pressure, volume, and temperature are given at every point. AB is reversible isothermal process, AC is reversible process. So these all are given to you. Now choose the correct options. Multiple options are correct. So let's see. First, isothermal. So if AB is isothermal, the temperature will remain constant along the curve AB. So T1 will be same as T2. This is T1 and the point B has temperature as T2. So T1 will be same as T2 because AB is isothermal process. That's the first thing. Second thing, AC is adiabatic. AC is adiabatic. Now, it's expansion because as you see the volume is increasing. So this is example of expansion. AB is also expansion, AC is also expansion. Both are expansion curves. Now, if it is expansion, then the final volume will be more than the initial volume. So I can say that V3 is more than V1. I can say that V3 is more than V1. So if V3 is more than V1, it's expansion. But we have learned that an adiabatic expansion causes cooling. The previous lecture I gave you, but this point under the adiabatic process. Adiabatic expansion causes cooling. If adiabatic expansion is taking place, then temperature falls. That means it's cooling effect. So adiabatic expansion causes cooling, and that means the final temperature will be less than the initial temperature. So we can say that T3 is less than T1. T3 is less than T1. So T3 is less than T1. That is final temperature is at C, T3. Initial temperature is T1, that is at point A. So T3 is less than T1 because AC is adiabatic expansion. Option B, if you look at, they have given T3 is more than T1. So this is wrong because T3 is less than T1. In cooling, temperature will fall. So T3 is less than T1. T1 is equal to T2. Yes, this is correct. Just now we discussed because AB is isothermal. So whatever temperature is at point A, same temperature will be at point B also. C option. Let's come to option C. Delta U along AB is more than delta U along AC. AB is isothermal, AC is adiabatic. Let's apply the formula of delta U. Now, delta U along AB is 0 because for isothermal process, delta U is 0. If temperature remains constant, delta U is 0. What is delta U? Delta U is change in internal energy. There is no change in internal energy for an isothermal process. So delta U is equal to 0. But if we look at AC, AC is adiabatic, then I'll apply the formula delta U is equal to NCV delta T. This is the formula for delta U. So delta U is equal to NCV delta T. What is delta T? Delta T will be final temperature minus initial temperature. Delta is always final value minus initial value. So T3 minus T1, which is the value of delta T. Just now we discussed that T3 is less than T1 because adiabatic expansion causes cooling. If T3 is less than T1, then NCV T3 minus T1 will be a negative value. That means delta U is a negative value for the curve AC. So along AB, delta U is 0 and along AC, delta U is negative. Since 0 is more than a negative value mathematically, we will say that delta U AB is more than delta U AC, because along delta U AB it is 0 and along delta U AC it is a negative value. So 0 is more than a negative value, and that's why delta U AB is more than delta U AC. So option C is correct. So this is a correct option. Why correct? Because 0 is more. Option D. Look at option D. For option D, we need to again draw the curve and analyze. So I've drawn the curves again. Right? So AB is a reversible isothermal process and AC is a reversible adiabatic process. But both are expansion curves, because in both cases, if you see the direction of arrow, the arrow goes from left to right. If it is going from left to right, it means it is expansion. This is the direction of the arrow. So the direction of the arrow tells you whether it is expansion or compression. Here it is expansion because the arrow is going towards the downward direction or from left to right. So both curves are expansion curves. If both curves are expansion curves, we know that work done in expansion is negative value. That is the convention followed in thermodynamics. If you look at the conventions, point here. So in convention, this is the convention. This is the convention. Fifth point, if work is done by a system, the work is negative. Also look at the seventh point at the same time. During expansion, the work is done by the system. During expansion, work is done by the system. So if work is done by the system, then the value of W is negative. If work is done by the system, the value of W is negative. And expansion means work is done by the system. So if we come back to the graph, I can write that along AB also the work is negative, and along AC also the work is negative. Right? Along AB also the work is negative, along AC also the work is negative. Now remember one more point, the area under the PV curve, magnitude of the work done. The area under the PV curve gives you the magnitude of work done. Magnitude means what? The modulus value. So if I look at the area under AB, the area is higher. This area is higher than the area under AC. The area under AB is higher than the area under AC. So this is the area under AC, and the larger part is the area under AB. So the area under curve AB is larger than the area under curve AC. But what is the area telling us? What is the area telling us? The area is telling us the value of modulus of work. It is not telling us the work. It is telling us the value of modulus of work. That means I can say that this W modulus of WAB is more than modulus of WAC. Modulus of WAB is more than modulus of WAC, because area under the curve gives you the value of modulus of work done. So this is what I can say. Also, because it's expansion, I can say gas along AB is more than work done by gas in AC. So gas is doing the work here because it is expansion. So I can say that because the modulus values are in this manner, the modulus value also tells me the work done by the gas. So I can say that the work done by the gas in AB is more than work done by the gas in AC. So work done by the gas in AB is more than work done by the gas in AC. But said that this is modulus value. This is not the actual value. The actual value of WAB will have a negative sign and the actual value of WAC will also have a negative sign. So it is like this. If I say mathematically that -3 is more than -5. So -3 is more than -5. But I can say modulus of -3 is less than modulus of -5. So the modulus values will be, the comparison will change, or the order will change if I take modulus values of negative numbers. So if I similarly extend this analogy to the work done in this case, I can say that means work done along AB will be less than the work done along AC. Why? Because the modulus values of work done are in this manner. The modulus value of work done of AB is more than the modulus value of work done along AC. Therefore, work done along AB will be less than work done along AC if I compare along with the negative signs. So this is the conclusion. Also at the same time, the conclusion. So what have we learned? What have we concluded? We can conclude that if they're asking us just work, they're not specifying by the gas, they're just saying where is work done larger, then we will compare along with the signs and we will say that this is the answer. Just this is the answer. Why? Because they have just said where is work done more or where is work done less. If only that much is asked, then I can say that this is the answer. That is WAV is less than WAC. But if they ask in which case is more work done by the gas, that means if the word by the gas is mentioned, then I will say that the modulus value of work along AB is more than the modulus value of work along AC. So the work done by gas in AB is more than work done by the gas in AC. So if they just mention work, then do not take modulus. But if they say where is work done by the gas more, if they mention the word by the gas, then we have to take the modulus values and then compare. So coming back to the options. So work done by the gas in AB is more than work done by the gas along AC. Yes, E is correct, but D is incorrect. D is incorrect because D just says work. So work done along AB is more than work done along AC. That is wrong. Why is that wrong? Because just now we established that work along AB is less than work along AC. So the correct options are A, C, and E. These are the correct options. Any doubt anybody has? Any doubt? Anybody has any doubt? Okay. Now don't write anything. Just listen, and if you have doubts, you can ask. Don't write anything now. After I send you the PDF, you start writing. Don't write anything now. Okay. So now coming to the closed cycle. So if I come across a graph, PV graph. So PV is pressure versus volume graph. Y-axis is pressure, x-axis is volume. Now look at the arrow. If I have an arrow of this kind, if you look at the first one, this arrow is nothing but going in the clockwise direction. If I look at the second graph, here also if you see the direction of arrow is in the clockwise direction. Just remember that work is negative for a clockwise cycle. So you have to remember this. The sign of work will be negative if you go in a cyclic process in the clockwise direction. So what is clockwise? Both are clockwise. This is also clockwise. This is also clockwise. Both are clockwise. Similarly, if I have a cyclic process in the anti-clockwise manner. So if it is like this is called anti-clockwise. This is also anti-clockwise. This is also anti-clockwise. Both the graphs that you see currently on the screen are for anti-clockwise cycles. So the value, the sign of work will be positive for anti-clockwise cycles. Proofs are not required. Why? Because if you calculate, you will understand. If I give you values and then show the calculations, then you can understand. But that is not required. Just remember this as of now. That if I go along the clockwise manner, then the work done will be negative, and if it is in the anti-clockwise manner, then the work will be positive. Without values, we will not be able to prove anything. I'm just showing you in general now. No value has been given. But they can ask you as an MCQ, so we should know this. Okay, next part. Now we will get into a little bit of physics, and then we'll again come back to chemistry. So a little bit of physics we'll have to do now. So now in thermodynamics, the phrase potential energy of a gas refers to the energy associated with the intermolecular forces of attraction present in gas. So if there are intermolecular forces of attraction, then we see that the gas has potential energy. But in this chapter, we are dealing with ideal gases. We are not dealing with real gases. All calculations are based on the assumption that the gases are ideal. So we can say that since in an ideal gas there is no intermolecular force, the potential energy of an ideal gas is zero. You can say this. So the potential energy of an ideal gas is zero because in an ideal gas there is no intermolecular force of attraction or repulsion. Hence we say that the potential energy of an ideal gas is zero. Now, next concept, this is something new, as I said, this is a part of physics. Degrees of freedom. Now, a gas molecule has three types of motion. Three types of motion. One is translational, one is rotational, and one is vibrational. These are the three types of motion associated with the gas molecules. What is translational? If the molecule is going like this, This is called translation. Like rectilinear motion. Translational, it is going straight between 2 points. The direction of movement is like this. So if the movement is like this, it is called translation. Because it is moving in this way, it will have some kinetic energy. So that kinetic energy is called translational kinetic energy. Ke means kinetic energy. So translational kinetic energy is one type of kinetic energy. If the gas moves in a translational manner.
So can you please give an example?
Example is this. So if from this point to this point, if it is going, this is called translational motion from here to here. Right? Similarly, again, if it goes from here till here, again, it is an example of translational motion.
Okay.
Rotational. This is simple. Molecule may rotate like this. Rotation. It is rotating. Right? Or it may rotate like this. That is, the axis of rotation will be different. Right? It can rotate along x-axis, it can rotate along y-axis, it can rotate along the z-axis. Because this is a three-dimensional picture that we are looking at. Right. Now, don't say translational is opposite of rotational. Don't use that word opposite. In what sense is it opposite? You cannot say opposite. These are three different types of motion. Translational is just movement between 2 points. That is called translation. Rotational is the movement along any axis. So if it is moving, that is without moving distance-wise, it is just moving along the axis. That is called rotational. If you may rotate your hand or you may rotate your finger and see, right? So it can rotate along x-axis, it can rotate along y-axis, it can rotate along the z-axis. And the last type is vibration. It is due to vibrations, molecular vibrations, right? But vibrational kinetic energy is not being considered in our examples or in our numericals because vibrational kinetic energy is significant only at very high temperatures. So we will ignore vibrational kinetic energy for all calculations in chemistry. But yes, the first two are important. Now, what is the meaning of degrees of freedom? It is the number of independent terms in the expression for kinetic energy. So if I want to write the expression for kinetic energy, I can say that the kinetic energy is due to the translational kinetic energy plus the rotational kinetic energy. Vibrational is ignored, so forget it. I can write terms like this one by one. I can add up total kinetic energy. If I want to write, I will write on the kinetic energies for translational part, and also I will write down the kinetic energies for the rotational part. So half mv square is for the translational part and half I omega square is for the rotational part. So I'll write different formulae for the kinetic energy, rather total kinetic energy. Now, the number of terms that I'm able to write, the number of terms that I'm able to this expression of kinetic energy is called the degrees of freedom. Let's do the example, then we'll understand. Case 1, monoatomic gases. A monoatomic gas has translational motion along three axes. See, even translational motion can be along three different axes. Why? Once it can move like this, once it can move like this, once it can move like this, right? Translational motion can also be along three different axes, that is x, y, and z. So one is this way, one is so x-axis, y-axis, z-axis, because you know that the three axes are in three-dimensional figure. So they are mutually perpendicular to each other, the three axes, that is x, y, and z. The molecule can move along any axis, like I showed just now. It can move like this, it can move like this, it can move like this. So it can have translational motion along any axis. So we say that translational motion is possible along 3 axes. Total, if I say that the possibilities, if I look at, then there are 3 axes, right? There are 3 axes. So I'll write monoatomic gas has translational motion along 3 axes. What are the 3 axes? X, Y, and Z. And also it has rotational motion, which is negligible as the atom is a point mass. The size of atom is small. Because it's monoatomic, I will say it has only one atom. Focusing on only one atom because the gas is monoatomic. This point mass, that is very small mass, will rotate. I'm not saying it will not rotate. It will definitely rotate. But the rotation will be in such a way that you can ignore that part because it is extremely small. Now, if I go into the depth of physics, you will see that there's a concept of half I omega square in rotational motion. So in physics, there is a chapter called rotational motion, and then you come across this term, half I omega square. So for a monoatomic gas, because the atom is extremely small and there is only one atom, if I consider the value of half I omega square, it will be extremely small and it can be ignored. So I say that the rotational motion of a monoatomic gas is negligible. So I will just consider the translation of the monoatomic gas, as a result of which I will say that since there are 3 axes along which the translational motion is taking place, the degrees of freedom is equal to 3. Small f is the symbol for degrees of freedom. Number of degrees of freedom is equal to 3. DOF stands for degrees of freedom, also denoted by F, that is small f. Number of degrees of freedom is 3 for a monoatomic gas. The value of CV, that is capital C small v, that is molar heat capacity at constant volume, is 3 by 2 R, because the formula for calculating CV according to physics is 1 by 2 FR, where F is the number of degrees of freedom. So CV is equal to 1 by 2 FR, and the value of F is 3. I'll put the value of F as 3, I'll get CV is equal to 3 by 2 R. Right? So CV is equal to 3 by 2 R for a monoatomic gas. This is how you get, this is the derivation. So if they ask you how many degrees of freedom are possible for a monoatomic gas, we'll say there are 3 degrees of freedom. Which 3? The translational motion, the kinetic energy which is associated with the translational motion along 3 axes, X, Y, and Z. What about the rotational motion? The rotational motion is negligible because the atom is a point mass and it is only a single atom that is there in our consideration. A single atom rotating does not create a very high amount of kinetic, almost nil, because rotation can be ignored because of its small size. Half I omega square, that term can be ignored. What is half I omega square? Half I omega square is a formula which tells us about the rotational kinetic energy. And I is called moment of inertia, and omega is nothing but the angular velocity. You will study these things in physics, or maybe you have already studied half I omega square in physics. Capital R is always gas constant whenever we write capital R in chemistry. That is 8.314 joule per mole Kelvin. So what is small f? Small f is the total number of degrees of freedom associated with any gas molecule. What is it telling us? It is telling us the different possible motion, different possible types of motion for a gas molecule. But because the gas molecule is monoatomic, only one atom is present. And if there is only one atom present, we can ignore the rotational motion completely. So we can just say that the degrees of freedom are due to the translational motion along the 3 axes. The rotation is completely ignored. Diatomic gases and linear polyatomic gases. See, a diatomic gas will be like this. One atom, second atom connected to each other. Like you have an oxygen molecule, right? So this is a diatomic gas. They are connected to each other via covalent bond. Similarly, linear polyatomic gases. If I talk about carbon dioxide is a linear molecule. Okay, so it's a linear polyatomic gas because there are three atoms. Now, linear, because it's linear, all three atoms are along the same straight line, the two oxygen atoms and the carbon atom, right? So, linear polyatomic gases and diatomic gases, for these we have again consideration, we are considering the translational motion and all these things. So, let's see. Now, a diatomic gas or a linear polyatomic gas again will have translational motion along three axes, but also it will have rotational motion along three axes, right? But But along one axis of spinning, the value is negligible because the distance from the axis of spin will be nil as the atom is a point mass. So what is this? Again, going back to physics. If I have, let's say, this as my molecule, this as the molecule, and if this is rotating, can I say that if I consider one axis as this, that is the horizontal, the same as the covalent bond. Okay. So if I consider that this is the diatomic molecule and this is the axis of rotation. As I said, there are three axes, X, Y, and Z. So if this is the axis of rotation, one possible axis, I can say that half I omega square will again come into the picture, right? Half I omega square will again come into the picture because it is rotating along this axis. Rotating along this axis means this way, right? This is the axis along which it's rotating. So this is the axis along which the molecule is rotating. If you see from the center of the axis to this point, that is a distance. This distance is almost negligible, right? Because as it is the atom is a point mass, as it is the atom is a point mass, on top of that, if you are considering only this portion, that is the radius of the atom, then it will be very small. So the half I omega square term will be very, very, very small. Hence, it is negligible as compared to the terms which are produced when the rotation axes are different. The rotation axes are like this also. Right? One of the rotation axis could be like this, vertical, like I've shown, because you have rotation along x also, y also, and along z also. So if this is the rotation, then this molecule is rotating like this, right? Like this. Fine, this is proper because from this axis, the distance is sufficient. Now there is no problem. So only along this axis, that is the horizontal one which I showed, along that axis only the term I omega square can be ignored. And so I can say that along one axis, only one particular axis of spinning, the value is negligible. The value is negligible because the distance from the axis of spin will be nil as the atom is a point mass and I can ignore the rotation along that axis. So I can only say that there are three axes along which translational motion is happening and two axes along which the rotational motion is significant. Two axes, not three. Although actually it is happening along three, but because I showed you that the term I omega square is extremely small, we can ignore that term, and so the rotation can be attributed only to two axes. So 5, 3 plus 2. 3 is for translational, 2 is for rotational. So 5 will be the degrees of freedom for a diatomic gas or for a linear polyatomic gas. CV is given by F by 2R. So put the value of F as 5. So you get 5 by 2R. Non-linear. Now if it is non-linear and other polyatomic gases, then all three types of rotational motion and all three types of translational motion can be considered, and now they can be ignored along any axis. So total number of degrees of freedom will be 6. Why 6? 3 along translational and 3 for rotational. So Cv will be F by 2R, F will be 6 for a non-linear polyatomic gas. Put the value of F as 6 and you get 6 by 2R as the value of Cv, that is 3R. Cv का formula F by 2R experimental है, you cannot derive that. That is experimental. These all are done through experiments. Just we are making things simple so that mathematically we can understand them. All are results of experiments. So Cv is F by 2R. You have to remember that Cv is F by 2R, and F, the value of F changes depending on whether the gas is monoatomic or diatomic or linear triatomic or linear polyatomic or non-linear polyatomic. Depending on all these different types of orientations of the gas molecules, you can have different values of degrees of freedom. Some more examples of linear polyatomic gases are nitrous oxide is N2O, C2H2 that is acetylene, etc. So you have to know the linear polyatomic gases. Okay, now see, somebody wants a repetition of the diatomic gas part, I guess. So coming back to diatomic gas. A diatomic gas has 3 types of translational motion. Which 3? One is along the x-axis, one is along the y-axis, and one is along the z-axis. That is translational. Translational is just rectilinear movement. That is movement from one point to another point. Coming to rotational motion, the molecule is rotating. It's a diatomic molecule. So the molecule is rotating. But the rotation also can be along any of the 3 axes. The rotation can be along the x-axis, the rotation can be about the y-axis, or the rotation can be along the z-axis. In fact, any such, because there are so many molecules in a sample of gas, so you cannot restrict its motion to only one particular axis. It can rotate along any axis as per its wish. But then the rotation is along axis, and if it is along a particular axis, you need to consider the value of half I omega squared because it is rotational motion. If you see, as I said, this is a diatomic molecule. If I draw the axis in this manner, definitely one such axis will exist. So along this axis, if I want to calculate the value of half I omega squared, that value of half I omega squared will be almost nil. It will be very, very small. Why will it be very, very small? Because this distance, that is from the center of the atom till the axis, okay, or till the other end of the atom, from this to this distance is extremely small, and because this distance is extremely small, half I omega squared can be ignored. Because as it is, the atom is a point mass. On top of that, you are seeing the distance from this part to this end. So this distance will be extremely small. Because what is I? I is moment of inertia. So it will change if the axis changes because the distance from the axis will change. Okay. So this is what we did. Now let's do one question. This will be better. Only this much is required for degrees of freedom. This is more than sufficient. You don't need to know anything apart from this for degrees of freedom. Now we'll do one question. It's a very, very important question. It's a typical JEE advanced type of question. So this is the question. Through this question, all your concepts will be clear. It's a graph. Capital V is volume, capital T is temperature. As I said, if nothing is mentioned in the question, you will assume every gas to be an ideal gas. This is the process. Arrows are shown. Arrow indicates the direction of movement. That is the process. Points have been marked. A, B, C, D are the points. You can look at the arrows also. And your P is given as 300 Kelvin. What are the things which are given here now? We see. Given. Given. First. The gas is monoatomic. Second. The ratios of volumes are given. A means at point A, B means at point B. These are the things which are given. Last thing which is given is these are the things which are given.
So could you see the last one?
You want to see the last point? Calculate. Calculate. What are the things that to calculate? First, temperature at point B. Second, heat exchanged in each process. Third, total work done. These are the things that you have to find out. It's a lengthy question because there are three subparts to this. So in the exam, you will get only one subpart. I have given three subparts so that we can understand the things better. But actually, it is a very lengthy question. I mean, such a lengthy question will not appear in any exam. Only one portion of this will appear, but so many parts cannot appear in the exam. So one single question cannot be so lengthy, right? That is why don't panic. This has been done by me. I have put three subparts because I wanted to show the calculations and the formulae. That is why I have taken three parts. But in the exam, you will get any one portion of this question. If such a long question is there, then you will have to calculate any one parameter, not more than one parameter for one question. Or it will be a paragraph type of question. So in that paragraph type question, you will have 3 to 4 questions for the same paragraph. So one paragraph is followed by usually 3 questions. That way it can be. Okay. So let's see now what are the things. Now stop writing and observe what I'm doing. Direction of arrow is extremely important because if I know the direction of the arrow, I know whether the process is from A to B or the process is from B to A. Accordingly, my initial and final values or the states will change. When I'm taking one process, then for that process, I must know what is the initial state of the system and what is the final state of the system. So if the arrow direction is not known to me, I cannot figure out which is the initial state and which is the final state. That is why it is very important to know the direction of the arrows. So let's see now. So A to B, look at the given data. A to B is isobaric. A to B is isobaric. Isobaric means what? The pressure is constant. Isobaric means the pressure is constant. Fine.
Sir, I got disconnected. Could you repeat what you just said? I got disconnected. Could you repeat what you just
Yeah. A to B is isobaric. That means the pressure is constant along AB. So I can use the gas laws. So let's start now here. For AB, like this I will show. For A to B, or let's say I'll show like this. Okay. For A to B, I can say that because it is isobaric, according to gas law, V1 by T1 is equal to V2 by T2. This is what I can say. Why I can say this? Because pressure is constant for A to B. On solving this, I can say that in the question it is given that VB by VA is equal to 2. It is given in the question. VB by VA is equal to 2. So VA by VB will be 1 by 2. TA is given as 300 in the question. If you look at the graph, it is given TA is equal to 300 Kelvin. On solving this, I'll get TB as 600 Kelvin. The first part was this. Any doubt? Yes. So I got the value. So everything is based on gas laws in this chapter. Fine. A to B I found out. They wanted me to find out the value of temperature at point B. So this is done. Coming to the second part of the question. Heat exchange in each process. Now this word, what does this word mean? This word means that I have to individually look at each process and then find out the value of heat. There are 4 processes here. A to B, B to C, C to D and D to A. Since there are 4 processes, I have to find out the value of heat for each process. So first, A to B. What is the symbol for heat? Q is the symbol for heat. Now A to B is what? Isobaric. For isobaric process last time, I told you that the value of Q is equal to delta H. For isobaric process, the value of Q is equal to delta H. And what is the formula for delta H? That also I gave. Delta H is equal to NCP delta T. So the formula need to be known. I'll put the values. What is N? Number of moles. Question has given me 2 moles. There are 2 moles of gas. Okay, one more thing is mentioned in the question. All answers must be in calories. Or rather, values of this is given in the question. Okay. Now the gas is monoatomic gas. It's a monoatomic gas. For monoatomic gas, Cv, Cp we know, right? Number of moles is 2. What is Cp? We know that for a monoatomic gas, Cv is equal to 3 by 2R. What is Cp then? We know that Cp is equal to Cv plus R. Mayer's formula. What is Mayer's formula? Mayer's formula is Cp minus Cv is equal to R. So Cp is equal to Cv plus R. Use that, you will get Cp value here. So Cp will be 5 by 2R. Delta T. Delta is always final minus initial. So it will be TB minus TA because I'm focusing on AB at the moment. So 5 into R, PV is 600 and TA is 300. Put the value of R as 2 calories per mole Kelvin. So answer is how much? 3000 calories. This is the answer for heat along AB, that is only A to B. So the value of delta H is Q here because the process is isobaric, and the value of that is 3000 calories. I use formula for delta H here. So delta H is 3000 calories. But delta H is same as Q. Why? Because it is isobaric. For isobaric process, delta H is same as Q. Question asks me to find out Q. Q is heat. But if the heat exchanged is at constant pressure, we call it delta H. Next, B2C. Now let's focus on process B2C. If I look at the graph, I'll be able to figure out. Can I say the line BC is parallel to the y-axis? The line BC is parallel to the y-axis. Since the line BC is parallel to the y-axis, I can say that the temperature along BC is constant because the x coordinate is not changing along BC. Right? Okay.
Sir, then this will be an isothermal expansion.
That means this is an isothermal expansion. So B2C, if you look at, you will see that the temperature is, how will I figure out that the temperature is constant? Because the line BC is parallel to the y-axis. See, I may not have drawn it very nicely, but in the actual question paper, you will be able to understand that the line is parallel to the y-axis. Similarly, CD is parallel to x-axis. And DA is again parallel to y-axis. Okay. So BC. BC is parallel to y-axis, and that is why I can say temperature is constant. That is why it is an isothermal process, because temperature is constant along isothermal process. So BC. So BC is isothermal. BC is isothermal. How do I find out Q for isothermal? I know that according to the first law of thermodynamics, delta U is equal to Q plus W. Also, I know that delta U is equal to 0 for isothermal process. So I can put the value and I can say that therefore Q is equal to minus W. Now, what is W? W is work done. Work done for isothermal process was given to you last time. If you look at the notes, you will see that work done is this. Minus 2.303 nRT log final volume minus upon initial volume. So it will be Pc upon Vb. The temperature will be V because B2C is isothermal, so I can write TB. So TB is same as TC, I can say. Okay? TB is same as TC because it's isothermal. For isothermal process, temperature is constant. So I can say this. This minus and this minus will become plus. Number of moles is 2 and N is given as 2 moles. R is given as 2 calories per mole Kelvin. TB is 600, We have found out T log Vc upon Vb. Now, Vc and Vb are not given in the question, but I can say that Vc is same as Vd. Why? Because the line CD is parallel to the x-axis. The line CD is parallel to the x-axis. So I can say that VC, that is the y coordinate at point D, is same as y coordinate at point C. So VC is same as VD. So instead of writing VC, I can also write VD because VC is same as VD. The line CD is parallel to the x-axis. So I will write, instead of VC, I can write VD. So I can write here VD upon VD. This is equal to now. How to calculate VD upon VB? Can I say VD upon VB can be calculated like this? If I say I have VD upon VA, if I divide that by VB by VA, so I can say that this is equal to, this gets cancelled and I'll get this. Right? So I can say that this is log VD upon VA upon VB upon VA. Why am I doing this? Because these values are given to me in the question directly. That is VD upon VA is given and VB upon VA is also given. So I can write the same thing like this. Come to the given data. The given data says VD by VA is 4 and VB by VA is equal to 2. Right? So I can say that VD upon VA upon VB by VA will be 4 upon 2. 4 upon 2, that is 2. So this value is 4 and this value is 2. 4 upon 2. Right? So this is equal to on solving this, log 2. In the last lecture, I told you learn certain values of log. I gave you in the previous video. Log 2 has to be learned. Similarly, log 3 also has to be learned. And log 7 also has to be learned. Log 2 is 0.3. So I'll put the value of log 2. So on solving this, I can get the value of this entire expression. Right? This will be in calories. Why? Because R has been put as calorie per mole Kelvin. This R value is 2. value will be 1658.2 calories on solving this. Now, next process, C to D. Right? So this is what? This is the value of Q. This is the value of Q for process B to C. So finally, I will say Q is this. This is for which process? This is for B to C. Similarly, this is for which process? This 3000 is for A to B. Next process, C to D. C to D is isocodic. Why isocodic? Because the line CD is parallel to the x-axis. The line CD is parallel to the x-axis. See? Hence, it is isocodic process. That means what? VC is same as VD. For isocodic process, how do we find out Q now? For isocodic process, Q is equal to delta U. This is given in the last lecture. And delta U is NCV delta T. Let's put the values. N is 2 moles. CV, what is CV? CV is for monoatomic gas 3/2R. Delta T will be final temperature, that is TD minus TC. On putting the values, 3 into R. Now what is TD? If you look at the graph, you will see that this line, that is DA, DA is parallel to the y-axis. Since DA is parallel to y-axis, I can say that the temperature is same along this line DA. So whatever temperature is at point A, same temperature will be at point D, because the line DA is parallel to the y-axis. Since the line DA is parallel to y-axis, I'll say that the temperature at point A is same as temperature at point D. So what is temperature at point A? 300. So I can say that temperature at point D is also 300 Kelvin. Similarly, I can say that the line BC is parallel to y-axis, so temperature at point B will be same as temperature at point C. So TB will be same as TC. And TD will be same as TA. Put the values. In calories, I want to get the answers. Minus 1800 calories. This is the value of Q for C to D. last process is D to A. D to A is what? D to A is again isothermal because the line D is parallel to y-axis. So Q is equal to minus W for isothermal process. W. W is this for an isothermal process. Since the process is going from D to A is my final state and D is my initial state. So it's log VA upon VD. That is final upon initial. Minus minus will go. So I'll be left with this. N is number of moles. R is 2 calories per mole. TD is 300 Kelvin because TD is same as TA. Log. Now VA upon VD. In the question, VD upon VA is given. If you look at the question, the value of VD upon VA is given as 4. So VA upon VD will be 1 by 4. Now I can say log 1 by 4 is nothing but log 4 to the power of minus 1. 1 by 4 is 4 to the power of minus 1. This minus can be brought outside the log. What is log 4? Now we know log 2 is 0.3. If log 2 is 0.3, 4 can be written as 2 log 2. Log 4 is nothing but 2 log 2. That is 2 into log 0.3. It is 0.6. You have to know the properties of logarithms. The value comes out to be minus 1658.2 calories. Okay. So this is for which process? This is for D to A. So we have found out all the values of Q. The last part. What is the last part of the question? The last part of the question asks you to find out the total work done. total work. Now remember, work is a path function. So I cannot just focus on A and A because I cannot say that A is initial and A is final and so the work done will be based on A only. No, I cannot say that. Because work done is a path function. What is path function? Path function depends on each and every path taken to reach the process or to complete the process. That means work done along AB, work done along BC, work done along CD, and work done along DA. All these need to be considered. Then only I can find out the value of total work done. So for total work, W will be equal to work done along AB plus work done along BC plus work done along CD plus work done along DA. This is how I can calculate the total work done. Okay. So we can say that the work done is a path function. Now I will solve this and send you the final answer. That is a PDF. So you can go through it. Kindly note down in your notebook whatever we have done today. Whatever has been done today, you have to note down that in your notebook. So maintain the notes properly and then send me on WhatsApp. Now, many of you have not shown me the previous notes. So those of you who have not sent me the previous notes, I mean the two PDFs which I had sent you, those of you who haven't copied from those two PDFs need to show me by tonight. So please finish copying everything that we have done so far in thermodynamics. Today we had the third lecture. So I want you all to finish writing till whatever we have done today. And those of you who haven't shown me the notes of previous lectures, please show me by tonight. You have to send me on WhatsApp.